In this session, we go through some more numerical problems in continuous functions. Consider the function integral part of x, that is the greatest integer function or step function, whatever you like to say. This has a peculiarity. This is continuous on r minus z and discontinuous on z. Discontinuous on z. That is what I mean to say is the function is continuous at a very integral value of x and continuous at a very non-integral value of x and discontinuous at a very integral value of x. How? Let us see. Suppose continuity on z. Let us check for it. Let n belongs to z. F of n is equal to n, of course. Integral part of n. The first condition, okay. Next, f of n from left, that is left hand limit. Left hand limit. So, as n tends to infinity, as x tends to n from left, x is behind n. You observe the scene here. n minus 1, n plus 1. X lies here. At this juncture, x is n minus h or n minus something. Clearly, its integral part will be, what is the integral part of x which lies here? It is n minus 1. Hence, f of n from left is n minus 1, whereas f of n from right is f of n from right. In this connection, if you want to find f of n from right, there is a limit as x tends to n from right of f of x, then x is supposed to lie at this position, to the right of n. To the right of n means n plus something, n plus h, something like that, and its integral part is n. Hence, f of n from left and f of n from right are not equal. They are not equal. Hence, it's not continuous. It is not continuous. However, it is continuous from right. It has right continuity but not left continuity. A beautiful example of a function which has a one-sided continuity only. That is, it has right continuity at x is equal to n but does not possess the left continuity. That is, it is not continuous from left. As a result, it is discontinuous at x is equal to n. What is n? Any integer. Therefore, f is discontinuous on z. That is, it is discontinuous at every point of z. This is the discussion about the continuity of the function on z. Is it continuous? No, it is not continuous. Well, let us now think of the nature on r minus z. What happens? Continuity on r minus z. Continuity on r minus z. Okay, let us take an arbitrarily selected point in r minus z. Let a belongs to r minus z. That is, a is a real number but is not an integer. Let us observe this. Even though a is not an integer, as it is a real number, it is supposed to lie between two integers. It is supposed to lie between two integers, say n minus 1 and a. Automatically, integral part of a is n minus 1. Now, we like to examine the continuity of f at x is equal to a. For that purpose, as we all know, we may have to find three quantities. Number one, f of a from left and f of a from right. Let us now find them. What is f of a? What is integral part of A? I am supposing that A lies between two successive integers, namely n minus 1 and n minus 1 and n, say. In that case, integral part of A is n minus 1. Okay, what is f of A from left? What does it mean actually? Limit of f of x as extends to A from left. In this case, who is left to whom? X is left to A. To A. That is, left side of x means somewhere else here x lies. It is A minus h, say, something. See, the integral part of this A minus h is also n minus 1. Why? Because the integer less than A is n minus 1. The integer less than A minus h is also n minus 1. Therefore, here also it is n minus 1. Success. F has left continuity at x equal to A. Why? Because f of A is n minus 1. And lastly, f of A from right. That is, limit of f of x as extends to A from right, you are now going to have. So, to calculate that, in what way should you imagine x lies to the right of A? X lies to the right of A. Okay, what will be the nature of x at that juncture? A plus something. A plus something means A plus 10, A plus 100, A plus 1000. Like that? No. A plus very minute quantity, that is A plus h. Even for this A plus h, that integer which is less than that is n minus 1. The nearest integer less than that is n minus 1. Therefore, f of A from right is also n minus 1. You observe these three things. F of A from left, f of A from right, they are becoming equal. Therefore, what can you say? F is continuous at x is equal to A. And for all A belongs to R minus Z, it is continuous. So, F is continuous on R minus Z. Another important function, consider f of x is equal to integral part of x whole square minus integral part of x square. A peculiar problem, important problem, which has been asked for so many number of times in so many competitive examinations like JEE. Yes, of course, it's a good problem. How can you discuss with that? As we could explain in the beginning itself, this is a peculiar problem. Even though 1 is an integer, it is continuous at x equal to 1 and it is discontinuous at every other integer. This is the peculiarity, rather particularity, the speciality of this function. Yes, is continuous at x is equal to 1 and is discontinuous at every other integer. It is discontinuous at every other integer. Yes, that is to be remembered. Such a famous and useful problem it is. Yes. Let us now verify. How is it continuous at x equal to 1 and how is it discontinuous at every other integer? Let us verify. First of all, we see the continuity of the function at x is equal to 1. To examine the continuity at x is equal to 1, as we know, usually we may have to find three particular quantities, namely f of 1. What is f of 1? Integral part of 1 whole square minus integral part of 1 square. What is integral part of 1? 1. 1 square is 1. What is 1 square? 1. Integral part of 1 square is 1. 1 minus 1 is 0. Okay, f of 1 from left. That is, x is supposed to lie to the left of 1, isn't it? X is supposed to lie to the left of 1, somewhere else like this. So x can take at most 0.9999999 and so on. Its integral part is 0.999. Integral part is 0. 0 square is 0. Well, what is x? To the left of 1. It is in the shape of 1 minus h. 1 minus h whole square is also less than 1. It also takes the shape 0.999 and so on. Therefore, it is also 0. Integral part of 0 is again 0. 0 minus 0 is 0. Okay then, f of 1 from right. What is f of 1 from right? In this discussion, in this consideration, where should we consider x to be? Like this. X is supposed to lie to the right of 1. That is more than 1. And you can imagine x as 1.000001. That is, of course, 1 plus h. 1.00001. Integral part of 1.00001 is 1. 1 square is 1. Minus. Okay, 1.00001. You imagine that is in the form 1 plus h. What is 1 plus h whole square? It is also in the shape of 1 point something. It cannot go beyond 2, or it may not be nearer to 2. It is just above 1. Even 1 plus h whole square is, isn't it? Therefore, it is also in the shape of 1 point something, etc., etc., etc. 1 point something. Its integral part is again 1. Integral part of 1 is 1. 1 square is 1. 1 minus 1 is 0. Therefore, what did you notice here? F of 1 from left is 0. F of 1 from right is 0. F of 1 is 0. What can you say? Therefore, this is f of 1 from left is equal to f of 1 is equal to f of 1 from right. What will be our opinion? F is continuous at x is equal to 1, no doubt. Well, our observation is completed regarding continuity of f at x is equal to 1. Now it is our duty to check the continuity, to examine its nature at every other integer. Yes, as an example, we consider say 2, either 2, 3 like that, one of them. Because even if you consider some n which is different from, it can also be explained, but for the sake of convenience, let us have a known value, say so 2 or 3, some 2 we consider. Right, what is f of 2? As usual, okay, what are we discussing about? We are discussing about the continuity of that given function f of x is equal to integral part of x whole square minus integral part of x square. Okay, in this business, we could have already discussed with the continuity of f at x is equal to 1, and we have declared it that it is continuous at x is equal to 1. Now we have turned our head towards the continuity of f at x is equal to 2. In general, actually speaking, we have to test it for x is equal to some n different from 1. And for the sake of simplicity, for the sake of brevity, we are now considering x is equal to 2. Come on. Okay, what are the steps to be proceeded? 3 steps. What are they? F of 2, f of 2 from left, f of 2 from right. 3 things we may have to find. First of all, f of 2. What is f of 2? Integral part of 2 whole square. What is integral part of 2? 2 square. Integral part of 2 square. 2 square is 4. Integral part of 4 is 4. 2 square is 4. 4 minus 4 is 0. So f of 2 is 0. Okay then, f of 2 from left, what can you say? So in this discussion, where should that x is supposed to lie? X is just below 2 or behind 2 or less than 2. As we are finding limit of f of x as x tends to 2 from left, who is left to whom? X is left to 2. So it takes the form 1.9999 and so on. 1.99999 and so on. Okay, imagine 1.999 here. Integral part of 1.999 is 1. 1 square minus. Imagine x in terms of 1.999999. 1.999999 whole square. What is that? It is around 3.9999, etc. It's a very easy matter to estimate. 2 square is 4. 1.99999 whole square is just less than 4. That is, it takes the shape 3.9999 and so on. And its integral part is 3. 1 square is 1. 1 minus 3 is minus 2, not 0. Here itself, we have seen that f is discontinuous at x equal to 2. Why? Because left continuity is failed here. We are not able to see and say that f is continuous from left. Therefore, f is discontinuous at x equal to 2. Well, my dear, this happens to every integer. Even if you consider that x is equal to 3, this will be left hand limit is 3 minus something whole square, that is 3 minus something is 2, 2 square is 4, and there it is 8 point something, etc., etc. Then also it is not 0. So for 4, for 5, for n, for any integer n, the same thing may happen. It's not like that. It happens. Therefore, f is discontinuous at x is equal to 2 or 3 or 4 or 5 or any integer different from 1. Okay, of course, we have declared the answer that it is discontinuous. Of special interest here is the case to deal with the f of 2 from right. Of course, at this juncture, we have seen that it is discontinuous at x equal to 2. Why? Because 1 minus 3 is minus 2. This is minus 2, not equal to 0. Hence it is left hand limit is minus 2. And right hand limit, what do you say about the right hand limit? While calculating this limit, where should we imagine? Come on, tell me. Where should that x lie? It should lie above 2 or beyond 2, that is more than 2. It takes the shape 2.2 plus h, where h is a minute positive quantity. Or even, for the sake of example, 2.0001, you take it 2.00001. What is integral part of 2.00001? 2. 2 square is 4. Minus 2.00001 whole square. It will be around 4.01 or 4.02, like that only. It is just above 4. Therefore, its integral part is 4. So 2 square minus 4, it is 0. So what could you observe? What can you state specially? Even though this function is discontinuous at x is equal to 2, it is continuous from right at x is equal to 2. It is continuous from right at x is equal to 2. And the same thing can be said in the case of every integer different from 1. By observing these things, we conclude at the end that this is a special function which is continuous at x is equal to 1, but not continuous at every other integral value of x. Okay, what do you say about the nature of the function at r minus z? I like to consider, or I like to test the continuity at x is equal to 1.6. What is your opinion? Surely it is continuous at x at every other non-integral value of x. Yes. So this is continuous on r minus z union 1. Okay, that is the specialty of this function. Let us now look at some more special examples. F of x is equal to e power x. F of x is equal to a power x. f of x is equal to k f of x is equal to sin x, f of x is equal to cos x, f of x is equal to tan x for all x not equal to 2n plus 1 into pi by 2, etc., etc. These are the most general functions which are continuous respectively on their domains. Continuous on R, continuous on R, everywhere continuous. If a particular function is continuous at every point of the domain, we say that it is everywhere continuous. And we know that the domains of all these functions till this one is real numbers. So continuous on R, continuous on R, continuous on R, continuous, and here it is continuous in its domain. So it is not continuous at x equal to pi by 2, x equal to 3 pi by 2, x equal to 5 pi by 2, and so on. Tan x has a peculiarity because that pi by 2 is not involved in the domain, isn't it? Let us observe the nature of tan x, say at some pi by 2. What happens? Very first thing is the function is not defined at x equal to pi by 2. Moreover, x tends to pi by 2 from left. If you consider the limit, it is plus infinity. You observe the graph, it goes up. If you observe the limit as x tends to pi by 2 from right of tan x, it is minus infinity. So, the three conditions are failed. F of pi by 2 is not defined. F of pi by 2 from left, f of pi by 2 from right, they're just it is a customary symbol. One is plus infinity and another is minus infinity. So it is foolish to test the continuity of tan x at x is equal to pi by 2, similarly at 3 pi by 2, similarly at 5 pi by 2, and so on. As moreover, viewing all these things, there are some more functions, say log 1 plus x and like that. They are respectively continuous in their domains. Of course. Yes, these are the standard functions. One more thing is f of x equal to x, identity function, continuous. F of x equal to x square plus 1, f of x equal to x cube plus 3, f of x equal to a naught plus a1x plus a2x square plus a3x cube, etc. n x power n. Every polynomial in x where the coefficients a0, a1, a2, a3, etc. n are all real numbers is continuous. That is, every polynomial is also continuous. If at all you look at f of x is equal to x plus 1, then it is continuous on R. Well, regarding these polynomials, if some restrictions have been put, it is a special job, of course, to test the continuity of the function at those particular points. And we shall come across such functions in the next discussion, in the coming discussion, in due course of time, within minutes. Regarding polynomials involved in different problems, there might be a special discussion to the continuity. Let us now observe one such function. Consider the function. F of x is equal to 1 plus x square for all x less than 0. f of x is equal to 1 for all 0 less than or equal to x less than 2, and 2x plus 1 for all x greater than or equal to 2. At three different junctures, it has been defined in three different ways. Let us observe the nature of the function graphically. Or pictorial explanation. This is 0. Consider. In this region, f of x is equal to 1 plus x square, including 0 up to 2, including 0 and up to the region less than 2. The definition, f of x is a constant function, f of x equal to 1. After 2, f of x is equal to x plus 1. Well, what is the question actually? Discuss with the continuity of f on R, an entire set of real numbers. What is your comment on the continuity? Well, you observe this region. In this particular region, f of x is a polynomial of second degree, surely continuous. In this region, f of x is a constant function. We know that every constant function is continuous. Hence, f is continuous in this region also. Okay, let us go beyond 2. In this region, even from 2 to infinity, f of x is a linear polynomial. Of course, a polynomial of first degree, that is x plus 1. Hence, it is continuous. Okay, in 3 different regions, f is observed to be continuous. Then where should we feel doubtful? At only 3 junctures. What are they? At 0, at 2, only 2. At these 2 points, you may have to test. Okay, let us test at 0. What is f of 0? 1. F of 1, f of 0 from left side is definition. 1 plus 0, 1. Happy. Again, let us look at f of 0 is 1. F of 0 from left, as it is left to the left of 0, 1 plus 0 square, 1. F of 0 from right, more than 0. This is the region, and in this region f of x is a constant function, up of course 1. You please observe these 3 items. F of 0 is 1, f of 0 from left is 1, f of 0 from right is 1, and f is continuous at x equal to 0. We feel happy, we should feel happy. F is continuous here, here and here also. So up to this point, for continuity of f, there will be no obstruction at all. Now it is our duty to check or test the continuity at x is equal to 2. Let us see. What is f of 2? 2 2s are 4, 4 plus 1, 5. What is f of 2 from left? 2 from left is this region. It is 1. Enough. The scene is, the picture is very clear. The scene can be seen very easily as it is not having left continuity. F of 2 is equal to 5, but f of 2 from left is 1. So it is discontinuous at x equal to 2. However, f of 2 from right, let us now find it. F of 2 from right, what do you say about it? 2 from right means more than 2. X is supposed to lie here. X is supposed to lie here means it is supposed to satisfy this function. That is, f of 2 is, it is 2x plus 1, not x plus 1. What is f of 2 from right? 2 2s are 4, 4 plus 1 5. What is your comment? What is your comment? Even though f is discontinuous at x is equal to 2, it is having right continuity at x is equal to 2. It is having right continuity at x is equal to 2. Well, observing all these things, what should be our conclusion? In this region it is continuous, at x equal to 0 it is continuous, in this region it is continuous, and except at 2 all the other real numbers, at all the other real numbers f is continuous. So by concluding this, as the last sentence we write f is continuous on r minus 2, except at x is equal to 2 it is continuous. Except at x is equal to 2 it is continuous. So you are supposed to observe the continuity of polynomials as and when they are involved at different cases like this. Yes, continuity of f is observed here on entire set of real numbers except at 2. Except at 2, x is equal to 2. Yes, next one. In the previous discussion, we have missed one more function, that is f of x is equal to mod x. Is always continuous at x is equal to whatever real number you say. It is continuous on r. It is continuous on r. Well, let us now examine some more functions in which this modulus function is involved. What about it? F of x is equal to mod x minus 1 plus mod x minus 2. Mod x minus 1 plus mod x minus 2. What do you say about this? Is it continuous at x equal to 1 or x is equal to 2 or any other real number? Is it continuous? Let us test. You see, f of x is equal to, let us now divide this into 3 different regions. What are the regions? X less than 1, 1 less than or equal to x less than 2, x greater than 2. Let us define. If x is less than 1, come on, here it is, x 1. What is the distance between x and 1? Do you say that it is x minus 1 or 1 minus x? 1 minus x. Therefore, mod x minus 1 is 1 minus x. X is less than 2. What is the distance between x and 2? Is it 2 minus x or x minus 2? 2 minus x. So it is 2 minus x. Altogether it is 3 minus 2x. Now, 1 less than or equal to x less than 2. 1, 2, x. Observe the picture. Where does x lie? Above 1 and below 2. Well, is x less than 1 or greater than 1? Greater than 1. Distance between x and 1, that is mod x minus 1. It is x minus 1 or 1 minus x? X lies above 1. What is the distance between x and 1? Do you say x minus 1 or 1 minus x? Here, x minus 1. So, mod x minus 1 is x minus 1. Okay, what do you say about x and 2? It lies below 2, that is behind 2, that is less than 2. What is the distance between x and 2? Do you want to say x minus 2 or 2 minus x? 2 minus x. So it is 2 minus x. X and go away, leaving you 1. Leaving you 1. The last case, x greater than 2. In this case, greater than or equal to 2. 1, 2, here x lies. So, to mean or to have an explanation of the nature of the function f of x in this case, x lies above 1 and x lies above 2. What is the distance between x and 1? Why I am always considering distance between? Modulus function is just nothing but the distance function, isn't it? What do you mean by mod x minus 1? It is nothing but the distance between x and 1. Well, in this case, x lies above 1, Therefore, the distance between x and 1 is x minus 1. Hence, this is x minus 1. Automatically, that is also x minus 2. Altogether, this is 2x minus 3. 2x minus 3. As this is the case with the function. Well, as before, let us now observe pictorially. This is 1. This is 2. X less than 1. In this region, it is 3 minus 2x. Between 1 and 2, it is 1. Above 2, it is 2x minus 3. Below 1, polynomial, linear polynomial, continuous. Between 1 and 2, constant function, continuous. Above 2, linear polynomial, continuous. So if at all you feel any doubt, you may doubt at 1 and 2. Okay, 1. What is f of 1? 1. What is f of 1 from left? 3 minus 2. 1. F of 1 from right? 1 from right? 1. So all those three are equal. So it continues at x equal to 1. Similarly, you can easily observe that it is continuous at x is equal to 2 also. Surely, f of 2, what is f of 2? 2 2s are 4, 4 minus 3, 1. F of 2 from left? 1. F of 2 from right? 1. Hence, f is continuous on R. Like this, mod x minus 1 plus mod x minus 2 plus mod x minus 3, mod 2x minus 1 plus mod 3x minus 2 plus mod 5x minus 6 plus mod x. Wherever and whatever you like to have, you have in the definition of the function. It is continuous always on the set of real numbers. Well, when do we observe the discontinuity of the function in which modulus function is involved? It is a special case of interest. We shall now going to be deal with that. Now let us consider the functions written on the board. These have a special character. In every function, the definition occurs to be some p by q. It looks like rational form. The numerator contains modulus symbol. Denominator does not. Denominator contains modulus function, numerator does not. All the other things also present like that. These functions, for these functions, continuity will be broken at those points and in which the denominator becomes 0. For example, at x is equal to 1. Is it in the 0 by 0 form? As is modulus available everywhere or somewhere only? Somewhere only. Discontinuous at x equal to 1. 0 by 0 form? Yes. At only one place modulus function is available. Discontinuous. Similar. Discontinuous. Similarly, modulus is contained in the numerator but not in the denominator, and at x equal to 3 it is in the form 0 by 0. At x is equal to 2 is in the form 0 by 0. Discontinuous at x equal to 2. Discontinuous at x equal to 3. Discontinuous at x equal to 0. Of course, f of x equal to mod x by x is almost very nearer to the signum function. What is say about signum function? F of x is equal to 1 if x greater than 0, minus 1 if x less than 0, 0 if x is equal to 0. If you define f of 0 is equal to 0, it becomes signum function. It is surely discontinuous at x equal to 0. Left hand limit is minus 1, whereas right hand limit is plus 1, so it is not continuous at x equal to 0. Like that. We may have a generalization for those functions in which the definition occurs in the shape of a rational form and either denominator or numerator. Only one of them is this modulus function is involved, and at the point of discussion of continuity, it looks like in the 0 by 0 form. Then we say that it is discontinuous at x equal to that point. discontinuous at x equal to 1, discontinuous at x equal to 0, discontinuous at x is equal to 2, discontinuous at x equal to 3, discontinuous at x is equal to 0, x is equal to 0. Well, let us now view these functions in a different angle now. By following the previous sentence, we have constructed. Observe the function. It is also in the form p by q, that is rational form. Numerator does not contain modulus function, whereas denominator contains modulus function. It is in the form 0 by 0. And can we say that it is discontinuous at x equal to 0? No. There is some speciality. Why? Because x square is nothing but mod x whole square. Can you write like that? Why not? You can. So it is mod x whole square by mod x is nothing but mod x. Therefore, it can be f of x is equal to mod x for all x not equal to 0 and 0 if x is equal to 0. Surely continuous and at every real number. Actually speaking, f of x equal to mod x is continuous everywhere, and f of 0 is defined, of course. Therefore, it is continuous everywhere. Therefore, what makes this function to be continuous? The numerator contains x square. It's nothing but mod x whole square. So, mod x whole square by mod x is again mod x. Well, as x is not equal to 0, for that only this definition is valid. Well, after noting that, actually speaking, you need not specially mention this. Why? Because even if x equal to 0, this is 0. That sense can be conveyed here also. Okay, but it might be, as we are supposed to follow this restriction, we have to write like this. And f of x is continuous at x equal to 0 also. That is, f is continuous at every real number. That is, everywhere. F is everywhere continuous on R. F is everywhere continuous on R. Now, in most of the examinations, there is a general trend of questions that are being asked. There is a special model in continuity. What is that? We shall now discuss with that. Look here. If he himself is committing, giving that f of x equal to x sin 1 by x for all x not equal to 0 is continuous at x equal to 0. Of course, everybody knows that f of 0 is not defined here. And he has put that responsibility on your shoulders, of course, by making use of the data that f is continuous at x equal to 0. He is giving that f is continuous. You define f of 0 so that f is continuous at x equal to 0. You define f of 0. Well, what can we define? In order to satisfy the data, f must be continuous. So if you use the continuity, f of 0 is equal to limit as x tends to 0, x sin 1 by x. Every one of us knows that it is not an obstruction for us to consider the limit even though f of 0 is not defined. Moreover, in x sin 1 by x we are able to observe two functions. One is x, another is sin 1 by x. Limit of this first function as x tends to 0 is 0 and the second function is bounded. We could have already noted that f of x and g of x are two functions such that limit as x tends to a of f of x is 0 and g of x is bounded. Then the product f of x into g of x also tends to 0 as x tends to a. Here the limit of g of x need not exist, but you must be able to observe that it is bounded. Of course, the similar thing happens here also. In the place of f of x we have x here. In the place of g of x we have sine 1 by x here. Sine 1 by x is bounded. Everybody agrees with that. Minus 1 less than or equal to sine 1 by x less than or equal to 1. It is bounded between minus 1 and 1. So it is bounded and this tends to 0. Therefore, the product tends to 0. So what must be the answer? F of 0 is equal to 0. We could have defined f of 0. Of course, by making use of the condition which he has given in the data. What is the condition? F is continuous at x equal to 0. There are so many such examples. Let us see some few famous, rather standard examples. This is a famous question. At the same time, it is one of the easiest questions also to look at. Observe the function. F of x is equal to log of 1 plus x to the base c minus log of 1 minus bx to the base c by x for all x not equal to 0. As in the previous case, we are supposed to define f of 0 here also. What is f of 0? Of course, to define f of 0, you may have to use the condition which has been given in the data. What is given in data? It has been given that f is continuous at x equal to 0. Let us make use of it. What is the question actually? You are to find f of 0. Let us. F of 0 is therefore, what must be f of 0? Limit as x tends to 0 of f of x. Why? Because it should be continuous at x equal to 0 according to the data. According to the data, it must be continuous. That is why I am making use of the third condition in the definition of continuity. Okay. This is equal to limit as x tends to 0. Come on, friend. What is f of x? It has been given that ln 1 plus ax minus ln 1 minus bx by x. Now, let me split that into two things. Is equal to limit as x tends to 0 a into ln 1 plus ax by ax b into ln 1 minus bx by minus bx. Do you agree with that step? Is there any mistake? Does it make any harm to the step? No, not at all. This x can be distributed between these two. I have multiplied with a and I divided with a. Similarly, b and b. Why has this become plus? Plus into minus, minus. So no problem. Well, what do you want to have? This is 1 by ax into. So that everybody can believe that this is 1. Again, this is also 1. Because as x tends to 0, ax also tends to 0. As x tends to 0, minus bx also tends to 0. So, for the sake of brevity, I am making use of the standard limit. What is the standard limit? Limit as x tends to 0, ln 1 plus x by x is equal to 1. Do you doubt of this? Is there any doubt? 1 by x, if it comes here, 1 plus x whole power 1 by x. 1 plus x whole power 1 by x is e. ln e is 1. Like that. Okay. So, a into 1, a. B into 1, b. Totally, t is a plus b. What is the correct answer among the data? This is, of course, the correct option. Therefore, the right option, a plus b, the first option is the correct option. As it is a famous question, I have traced all the options also here. This is the way in which we define f of 0 or f of 1 or f of 2, whatever he may asks. Yes, there is one more such question. Let us see that. Now it is our turn to look towards the function f of x is equal to 4 power x minus 1 whole cube by sine of x by p into log of 1 plus x square by 3 to the base e for all x not equal to 0. And as usual, he is giving us that if e is continuous, that is the question. Of course, there are certain options. We can do nothing by looking at the options directly. Let us now make an attack to have the answer. If f of x is equal to 4 power x minus 1 whole cube by sine of x by p into log of 1 plus x square by 3 to the base e for all x not equal to 0. It has been given that it is continuous at x is equal to 0. By making use of that, we are supposed to find f of 0. That is, we are to define f of 0. As usual, what is f of 0? What is f of 0? Limit as x tends to 0 of f of x. What is f of x? There has been a bulkier expression here. Let us now make it very clear so that the limit can directly be obtained. The first one is 4 power x minus 1 whole cube. Now, I need x cube in the denominator, that's all. Put it first of all. Later on we shall decide. X cube. Simply by looking at sine x by p, you require x by p in the numerator. Have it first, later on we shall decide. X by p by sine x by p. Again, log of 1 plus x square by 3 is able to be seen here. To have a simplified form of this limit, we need x square by 3 in the numerator. Have it first of all. X square by 3 by log of 1 plus x square by 3. Now, the matter of settlement. There are so many things you could have introduced here newly. Let us see that all those which have been introduced are cancelled. X into x square, x cube and x cube go away, no problem. Here p into 3 is 3p. 3p comes in the denominator extra. So to cancel it, you may need 3p. This is the procedure. Okay. Now, imagine the limit. What is the limit of this part? We know that a power x minus 1 by x as x tends to 0 is log a to the base e. Therefore, it is log 4 to the base e, isn't it? What is that? Log 4 to the base e. So, this is log 4 to the base e whole cube. Why whole cube? It is just nothing but 4 power x minus 1 by x whole cube. That part comprises the limit log 4 to the base e. As whole cube is there, I am putting whole cube. Okay. X by p by sine x by p. What is the limit of this part? Theta by sine theta. You see, as x tends to 0, x by p also tends to 0, isn't it? As x tends to 0, x by p also tends to 0. Theta by sine theta is 1. Hence the answer is 1. Now, X tends to 0 implies x square by 3 also tends to 0. Therefore, this part, what is that part? You see, you recall the limit as x tends to 0, log of 1 plus x by x to the base e is 1. Does it look in this shape or not? It is surely. Of course, it is x by log 1 plus x. Whatever it might be, it is 1. Hence, this is 1. This is 1. 3p is there extra. So, altogether this is log 4 whole cube into 3p. This is the answer. This is the answer.